Hi everyone. Right now we're going to talk about the DC motors control. All right. This is on course module number 10, also the lab modules number 10, DC motors. And we intend to just make it very simple on the DC motors. We are not talking about the uh, brushless DC motors. We're talking about brush DC motors, right? And everybody knows the DC motor control is very straightforward. If you provide the power to the DC motor terminals, it spin on one direction, you reverse the leads, reverse the power, then the DC motor spins on the opposite directions. So to control the direction flow of the DC motor become very straightforward, you need an H-bridge. On the trainer board, you got 8 switches. 4 switches allow you to construct one H-bridge. So you got 8 switches. You are capable to do 2 H-bridges. Then you can control 2 2 DC motors. Allow the switch 1 and switch 3 on. Current flows to the coil one direction. And then allow 1 and 2 on, 3 and 0 off, the current flow opposite direction. So you control the leads of the FETs that allowed you to control the direction flow of the DC motor. Same thing at the second set, just different FETs. All right. And as we talk about from the stepper motors, all the FETs are controlled via the optical isolators. So you have a digital I/O through the logic ground. Then you will have the FET through the VCC, which is the power source. You can use any power source up to 2 amp, 5 volts, 10 volts, 12 volts, 24 volts. But keep in mind, limit the current down to 2 amp because the trace on the board, if you go more than 2 amp, it might burn the trace. But if you do need a higher amperage, the FET itself can handle up to 10 amp. Then you have to take the FET and mount it on a special heat sink, then resolder the wire to the FET. That's another way you can do. Even we have a heat sink on the trainer board, that's not going to be big enough to dissipate the heat. All right. So it's optical isolator, which is very necessary because the brush DC motors, when they spin, it generates a lot of sparks and it has a large contamination. It will affect the quality of the digital logic out of the controllers. So we have these built-in optical isolators. You really don't have to worry about it. Basically, just build that through the H-bridge. These H-bridges allow you to control the direction current flow to the DC motor. But enable for you to control the speed, you need to produce the pulse width modulation. Basically, you posit the control I/O in a very fast manner that you actually regulate the amount of energies going through the coil through the H-bridge. All right. Another thing I need to remind you when you use the H-bridge is if you ever turn the switch 0, 2, 1, or 3 on, which is going vertical, that means you got direct short. All right. It definitely burned the H-bridge, but burn the FET, but it definitely will not affect the logic side out of the controllers. And we will have a sample code when we do the lab. We're using the 16F84A by using the TMR0, which is the timer to produce different duty cycle in a very fast manner. So you can get up to 98% duty cycle or less than 50% duty cycle with those pulses that regulate amount of energies that equated to the speed of the motor spin. Then you send it out the different logic, you control the rotation of the shaft, then you mount the DC motors, they can do a lot of actuations. And we will have a live demo for the wireless remote control vehicles later. When you see that, that's exactly what we use to control the DC motors. And certainly we have another one, which is the camera mount on the stepper motor. So we actually use both. Since we only got 8 switches, so what we do is we separate them in DC motor or stepper motors. Okay, I'm going to stop here. Thank you.